Okay, picture this. You're about to spend, let's say, $1 billion on a single project. An AI project so massive, it's going to take a whole year to run. I mean, where do you even start planning something like that? Well, the answer isn't in some super complex code or a giant spreadsheet. It starts right here, on a napkin.
But seriously, how do you plan for something like that? You're talking about a project that's just burning through cash, tying up thousands of the world's most powerful computers for months. You can't just cross your fingers and hit the go button, right? One tiny miscalculation could literally mean millions of dollars down the drain.
And the answer? You'll love this. It's completely counterintuitive. You don't start by writing a single line of code. Nope. You start with probably the simplest tool you can imagine, a napkin. And this brings us to the hero of our story, napkin math. It's basically a set of surprisingly simple back-of-the-envelope calculations that act as the blueprint for these monster AI models. This isn't just doodling, it's the absolutely essential first step that figures out the time, the cost, and all the resources for the entire project. And this whole enormous, complicated problem, it really just boils down to two fundamental questions. That's it. First, how much work actually needs to get done? We call that compute. Just think of it as the total number of calculations. And second, how much space do I need to do all that work? That's memory, the actual physical room on the chip to hold all the numbers. So let's tackle that first question, right? Counting the compute. You might think the math behind AI training time is going to be insanely complex, but honestly, it's surprisingly elegant. It all revolves around a single number, just one, and that number is 6. Just kind of burn that into your brain for a second, because we're about to find out exactly where it comes from. Okay, here it is, the secret sauce. The total compute you need, that's the total number of calculations or flops, is roughly 6 times the number of parameters, which are kind of like the little knobs the AI can tune, multiplied by the number of tokens in your training data, which are basically just pieces of words. It's simple, it's powerful, and it is absolutely fundamental to everything. But that just brings up the obvious question, doesn't it? Why 6? Where on earth does that number come from? It feels kind of random. All right, so 2 of those 6 flops come from what we call the forward pass. This is really simple. It's just the model making a prediction. You feed it some data, and it takes a guess. That single guess costs about 2 flops for every single parameter in the entire model. But then comes the backward pass. And this is where the actual learning happens. The model looks at its guess, compares it to the correct answer, and sees how wrong it was. Then it adjusts all its internal knobs so it can do better next time. And this whole process of learning from its mistakes, it's way, way more computationally expensive. And as you can see, the backward pass is about twice as expensive as the forward pass. So let's do the math. We've got 2 flops for the guess and 4 flops to learn from the mistake. 2 plus 4, and there it is, our magic number, 6. See? Simple. Okay, so now we know the total amount of work we have to do. But how fast can our computers actually do that work? That's where this thing called MFU, or model flops utilization, comes in. It's basically a measure of your real-world efficiency. If a GPU is like a Ferrari, MFU tells you what percentage of its top speed you're actually hitting on the road. Anything over 50% is considered really, really good. And this number is a final piece of the puzzle to turn a giant flops count into actual days of training. All right, we figured out the work. Now we got to figure out the space. We need to size up the memory. And this is a very physical challenge. How in the world do you fit a digital brain with billions and billions of parameters onto a tiny little silicon chip? So what's eating up all that precious real estate on the chip? Well, it's mainly 4 things. First, you've got the model parameters themselves. That's the core knowledge of the AI. Second, the gradients. Think of those as the instructions for how to learn. Third, the optimizer states, which kind of help the model remember what it's learned so it can learn more efficiently. And finally, activations, which is just temporary scratchpad data that gets created during all the calculations. So yeah, that's a lot to cram in there. The next logical question is, okay, how can we shrink that memory footprint so we can fit even bigger models? Well, one of the most powerful tricks we have is playing with data precision. The standard is something called float 32. It's super precise, but it takes up 4 bytes for every single number. But for a lot of the work, we can get away with using bfloat 16. It literally cuts memory usage in half, down to just 2 bytes. Now, it's less precise, sure, but it keeps the range of numbers you need for deep learning. It's this crucial trade-off. Do you need perfect pinpoint precision, or do you need to fit a bigger brain? Making that call is key to efficiency.
And just like we had a magic number for compute, we have one for memory too. You guessed it, and that number is 16. Let's dig into why. So here's where that magic number 16 comes from. For every single parameter in the model, you need 16 bytes of memory. 4 of those bytes hold the parameter itself in high precision. Another 4 bytes hold its gradient. That's the learning instruction. But the biggest chunk by far, 8 whole bytes, is for something called the atom optimizer. It's super popular and effective because it keeps track of 2 extra numbers for each parameter to help the model learn smarter. But boy, does that memory add up fast.
Okay, so we have our rule of 6 for compute and our rule of 16 for memory. We have the theory. Now it's time for the fun part. Let's put it all together and see how these simple little rules can answer some truly billion-dollar questions.
And here we are, the napkin solved. So let's answer that first question, how long to train a 70 billion parameter model? We just plug our numbers into that compute formula, divide by the power of a big GPU cluster, factor in our efficiency, and we get about 144 days. Wow, that's almost 5 months of nonstop computing. Now for memory, what's the biggest model we can squeeze onto a standard server with 8 top-of-the-line GPUs? We just take its total memory and divide by our 16 bytes per parameter rule. And the answer? Around a 40 billion parameter model. I mean, look at that. With just 2 simple formulas, we have a strategic roadmap. It really is that straightforward.
And this is what's so incredible. These aren't just some clever thought experiments. These simple calculations are the absolute non-negotiable bedrock of multi-million, sometimes even billion-dollar AI projects. And hey, don't just take my word for it. The Stanford lecture this is all based on puts it perfectly. Efficiency is the name of the game. When these numbers get large, these directly translate into dollars. This napkin math isn't about saving a few seconds of compute time. It's about saving millions of actual dollars. So, at the end of the day, the big takeaway here is this. Understanding this simple math is way more than just a cool technical skill. It's the key that unlocks AI development at a massive scale. It's what makes these giant models possible, and more importantly, it's what makes them sustainable as they just keep getting bigger and bigger. Which really leaves us with a fascinating final thought to chew on. As these AI models continue to scale up to trillions of parameters,